So this week we're going to be discussing experiment 18, which is the Diels-Alder reaction. This is another very important reaction. It bears the name of two individuals, Otto Diels and Alder, and they won a Nobel Prize for this particular reaction because it's a very efficient way to form six-membered rings, and it forms carbon-carbon bonds in the process. So it's one of those few reactions that we have in our toolbox, so to speak, to make carbon-carbon bonds. It belongs to a class of reactions known as cycloaddition reactions, meaning it allows it to make rings, form a cycle. It also belongs to a class of reactions known as atom-economical reactions. It's very important that you read that science paper before coming to lab, because this is one of the hot topics over the last 20 years in chemistry, is dealing with atom-economical reactions. And what we're looking at with atom-economical reactions are all the atoms from the reactants are ending up in our product. So there's no waste. A number of the reactions that we've done, as you know, like SN2 reactions, you always have a leaving group that doesn't end up in the product, for example. And so you have to do something with those wastes. Well, ideally, chemists would like to be able to form their product by using starting materials that have all the atoms necessary to form that product with no waste. And so it's a lofty goal, but there are some reactions that actually do this quite well. Most of the addition reactions that we've learned about in class actually are atom-economical reactions. So for example, if we take an alkene, in this case I've got cyclohexene, if you add bromine to it, all of the atoms in the two starting materials end up in the product. There are no waste products that are produced from this reaction. Everything in the cyclohexene plus everything in the bromine ends up in the product, and so we would call that a very atom-economical reaction. Also, if we take an alkene and add water across the double bond, even though we have to use a catalyst as acid, all of the products, all of these starting materials, atoms from the alkene and the water end up in the product. And so it's an atom-economical reaction. Likewise, with the Diels-Alder reaction, it's also an atom-economical reaction because we've got a diene. We've got an alkene here, is the alpha-beta unsaturated ketone, and all of the atoms from these two components end up in our product very nicely. Let's talk a little bit about how the Diels-Alder reaction actually works. You have to have a diene and an alkene, or also known as a dienophile. The diene has to be in the S-cis conformation, meaning that around this sigma bond, that's where the S comes from, the two groups are cis to one another. This is not the favored conformation. Actually, we know that the S-trans, where the two groups are 180 degrees to one another, are actually favored at equilibrium, and so you actually have very little of this available in solution at any given moment. But nonetheless, we can close this reaction very easily, pushing arrows, and form our six-membered ring. So we've taken a diene, an alkene, we've formed a new six-membered ring. The important thing to note here is we're forming two new carbon-carbon bonds between carbons 1 and 6 and between carbons 5 and 4. And I'll just kind of bold those a little bit there so you can see which ones we're talking about. Now this reaction is a very good reaction. It typically goes to completion because it's favored by enthalpy. Notice what we've done here is we've started off with 3 weak pi bonds, and we only end up with 1 weak pi bond in the product. So that means we're gaining 2 strong sigma bonds, and that's what drives the reaction to completion. The fact that we're forming those very strong sigma bonds, that means that this process is enthalpically driven. It's driven by enthalpy. Also, if you look in your book, you'll note that the reaction actually proceeds not by the arrows that I'm pushing, but by frontier molecular orbital theory, which is what we're covering a little bit in class when we talk about this reaction. And that means that the highest occupied molecular orbital of the diene interacts with the lowest unoccupied molecular orbital of the dienophile, and they come together to form the product. So you have the highest occupied molecular orbital of the diene, the lowest unoccupied molecular orbital of the dienophile, and if we can get the energies close enough, those will interact with one another and actually form the product. That's a little harder to explain on the board, so to speak, and so it's a lot easier just to show arrow pushing as to how that reaction occurs. And so this is also a concerted reaction, meaning that all of the bonds are being formed at exactly the same time. So when we're coming together, we have no intermediates. We have a transition state, but we don't have any intermediates along the way. All these arrows are being pushed simultaneously. So let's talk about the exact Diels-Alder reaction that we'll be doing this week in lab. We are going to be using a molecule known as Anthracene. Okay. This is going to be our diene. This is also an aromatic hydrocarbon. It has 14 pi electrons, which satisfies Huckel's rule. And we're going to be able to do an addition with this quite easily. You'll look in your lab manual, you'll see the product from this. And then as our dienophyl, we're going to be using maleic anhydride, which has 2 electron withdrawing groups on it, which help lower the energy of the LUMO such that you get good HOMO-LUMO overlap that allows you to have the reaction to occur. Now, I'm not actually going to draw the product up here. I'm going to show you a model of it because it's just a lot easier to do than it is to draw. But what you should be asking yourself at this point is, how can we do an addition reaction to an aromatic hydrocarbon? Because we've learned that you can't do addition reactions to benzene, for example, and you can't do addition reactions to naphthalene very well, for example. But anthracene allows us to do this because in the product, we don't lose the aromaticity. If we do an addition to benzene, the product is not aromatic. Okay? And so that keeps that reaction from occurring because we know that aromatic things are more stable than what one would predict. However, in the case of anthracene, when we do an addition across these 2 carbons that I've got starred here, we actually end up with more aromatic character in the product than we had in the starting material. We actually end up with 2 isolated benzene rings in the product. And I'm going to show you that in the model. So this is actually what the product looks like. You can see we've got the 2 benzene rings. So we still have aromatic character in the product. We formed this 6-membered ring by the addition, and this is the part that comes from the maleic anhydride shown here. And so what you need to do before coming to lab this week is actually build a model of this and convince yourself of the NMR spectrum that is printed in the back of the lab manual. And so if you look at this, what you'll recognize is there's a mirror plane that runs through this part of the molecule, right through that central oxygen from the maleic anhydride. Okay, and so that means that certain hydrogens are going to be related to one another. But you need to also note that there's no mirror plane that runs this way that makes this benzene ring equivalent to this benzene ring. And so you're going to see some unique signals from both benzene rings that appear in the NMR spectrum, both the carbon NMR and the proton NMR. So look at the model before you come to lab and convince yourself of what type of signals one should see in the NMR spectrum that you have in the back of your lab manual. Okay? So let's just talk a little bit real quickly about the way the reaction is going to be performed this week. It's a very simple reaction setup. You're going to be using a tube, just a typical test tube to do this reaction. You're going to place your anthracene and your maleic anhydride in this tube with the solvent xylene. Xylene has a very high boiling point. You're only going to add a couple milliliters of xylene, so you're going to have a lot of empty tube, so to speak, remaining. And you're going to put this in your heating block or your sand bath, and you're going to heat that xylene up to its reflux point. Okay? And we're not going to have to use a reflux condenser because there's going to be plenty of tube above this. It has a very high boiling point. So the room air is going to actually allow the solvent as it comes up to recondense and fall back down in the tube. However, you need to be careful. If you see the reflux line getting too close to the top of the tube, we don't want the solvent to actually boil out. So what you would do then is take a paper towel and dampen it. Don't get it soaking wet. Get it wet, wring it out really good, just enough to make it damp. And you can rub the top of the tube with that damp towel to cool it down and bring that reflux line back down if needed. However, you do need to be very careful with this because anytime you touch a cold, wet towel to a hot object, it does have the potential of cracking, so make sure you pay attention to that. And also make sure that you don't get any water down into the tube. you'll cause splattering, and the water can actually react with the maleic anhydride, which we don't want to have occur. So as long as you have a reflux line somewhere in the middle of the tube, you don't need to worry about this. This is just a cautionary point in case for some reason your reflux line starts to get too close to the top of the tube. So make sure you read that science paper, look at that molecular model that you need to build with your model kit, and keep in mind the safety issues using a air condenser, so to speak,